Okay. So, let's see. What is the temperature of a gas once it's moved from a 10-liter tank at 22.6 atmospheres to a 5-liter tank? Let's make that 3 sig figs also, just so we don't have to worry about it. Okay. Alrighty. So here we go. I do have an announcement. We have a special visitor today. Let's see if she'll come up. If I have a treat somewhere in here. Usually I have treats in my desk, but of course not right now. Come here, Momo. That's right. Come say hi to everyone. Want to come up here? Or you want to go on the couch? Okay, she's going to go over there. But lo and behold, look. There we have her. One of my bigger dogs. So now you can see we have our special guest of the day. So she's just going to probably sit up there or want to leave the room, but she gets to learn gas laws instead. So let's take a look at this question then. So it is asking, oh gosh, we already have someone else trying to break through. Hi Kaz, hi Oz. Come here, dude. Okay. We're gonna have a whole parade of dogs in here, it seems, but that's okay. So this one we're dealing with changing conditions, right? And so we kind of have two formulas that we're going to use so far in our gas chapter, which were the ideal gas law and then the combined gas law, right? And we remember that the ideal gas law is better used for when we don't know a particular property, but we know the rest of them. And the combined gas law is good for when things are changing. So, which one do we think this one's going to fall under? Is this going to be finding a particular quantity when we know the others, or is something changing here? All right, Lamanda or Amanda, or let's see who else usually shows up to these. Give me an answer. Let's see if Momo's gonna try and get out of the room. Let's see. Combined, yes, I like that. Oh, Sherry, of course. How could I forget you? Okay, yes, so combined gas law problem, right? And Sherry got that because we can see that we have things changing here. And Momo has officially left the room, so that's the end of our special visit. So we all of 3 minutes. So, hi Maya, how are you? So, looking at this, let's go ahead and kind of look at all the numbers from this. We have 10-liter tank at a particular pressure, and we have a 5-liter tank at a pressure, and we have finally this initial temperature that's written here. So, looking at this problem, it looks like these two numbers here are going to be our initial conditions, right? We're starting in 10 liters and that particular pressure, and we are going to move it. Hi, Gumbo. We're going to move our gas to a different tank at a different pressure. So that would be a separate volume and separate pressure. And it's telling us also that our initial temperature was 26.2 degrees Celsius. So looking at these numbers, most of them are okay to use right now. However, that temperature, remember, we can't use temperature in Celsius for gas laws. So what we're going to have to do is convert this guy into Kelvin, right? And so that's going to be, oh gosh, so much math. 299.35 Kelvin. Alrighty, so it looks like we're solving for our second temperature. That would be the part that we're missing here. The question is asking what is the temperature. Since we already have T1, it's asking now for our final temperature, our second temperature. So we can go ahead and solve this equation for our second temperature. Again, if you want to know how I did that, I kind of did algebra, I guess would be the best way to describe it. Make sure you can do algebra like that, of course. Okay, so we can go ahead and plug in our numbers. So pressure 2 was 40.1. Volume 2 was 5 liters. Temperature 1, we just calculated. I can't fit the K in there, so sorry about that. The pressure 1 looks to be 22.6, and our volume 1 is 10. And so we would just have to plug in all this fun stuff. Okay, so that'll be 40. Oops. Oh my goodness. I can do simple math, I swear. 40.1 times 5 times 299 divided by 22.6 divided by 10. Okay, doing all this fun stuff, I get 265.57 Kelvin. Looking at all these numbers, we're probably going to have 3 sig figs. While I do not specify a unit, let's go ahead and give this in Celsius anyway, just for fun. Why not? So let's go ahead and see here. So if we were to convert that to Celsius, remember that Celsius would be the Kelvin minus the 273.15. (273.15) equals negative, I can do this, 8.42. I hope. I'm going to just double check that I don't want to give you guys the wrong answer. 265.57 minus 273.15. Nope. It's the opposite. Okay. I know how to do math, I swear. That's why I double check these things, right? And looking at that sig figs, it looks like we're just going to have to round this to negative 8 degrees Celsius. How exciting. So, cool. So I guess we would have done it even with my crappy calculations. We would have still gotten 8 degrees Celsius. So that works. So, that would be our answer. Hooray, we're done. And so, there we have it. We're good. Look, small ones here too. We had so many various dogs today coming in. And Creature's barking downstairs, so I think we might actually be out of earshot for once. So I don't have to go deal with him. Though if you can hear the barking, I can go if necessary. So there we have it. So really, this equation is going to be used for when you have something changing from an initial set of conditions to a final set of conditions. Just remember, you can never use Celsius directly for calculation for gas law stuff. But other than that, just whatever your units are, make sure they're the same. So whatever your pressure unit is, make sure that's the same. Whatever your volume unit is, make sure that's the same. And then temperature must be Kelvin. Cool. So if anybody has any questions on that, go ahead, drop them. And in the meantime, let's do another one. What's our favorite gas? How about chlorine? Let's just say at STP. This one will need a little bit of digesting for, but we can solve it. We have the tools. We just this one may not be as obvious to us as to how we're going to calculate it. But let's go through it step by step. So remember, density, it's giving us the units of grams per liter, right, in this particular problem. So the way of saying that is some amount of grams in 1 liter. So remember, that's how conversion factors work. We're going to make sure that our bottom one is always 1, right? That's how we make things nice and easy for us. So remember, grams per liter means per 1 liter. So that's what this is saying. So if we want to think about it, we have STP also, which we remember 0 degrees Celsius and 1 atmosphere. So really, we do have, in this, we have a temperature, a pressure, and a volume. And so this particular one is just asking us for how many grams in 1 liter of this gas at STP. Remembering STP is 0 and 1 for temperature and pressure, respectively. As always, we can't use this as is, so we'll go ahead and make that into Kelvin. And so looking at this, we have 3 quantities. We're missing a 4th. Nothing's changing here necessarily. So this is a situation for the ideal gas law, right? We have 3 quantities. We're looking for the 4th one. But which one are we looking for? From this, it looks like we have a volume. Looks like we have a temperature. And we have a pressure as well. And of course, we know what R is. R is a constant. So it looks like what we're missing here is moles. And so we do, of course, have the grams of a substance. That's what we're looking for. And so with our ideal gas law, we'll be able to solve for moles. And then we can convert from moles into our desired quantity of grams. And so, so we can go ahead and rearrange our ideal gas law so that we can solve for moles more easily. Pressure was 1 atmosphere. We have 1 liter. We have our gas constant. Oops. And we have our temperature. And so we can go ahead and do the math. So 1 over 0.08206 divided by 273.15 looks like we get 0.0446136 whatever moles. So remember again, this part, it does not matter that we have chlorine, right? Whatever gas we're dealing with, this will work for. So in fact, this would be how many moles of any gas we would have at STP. And so we would just need to change the density according to the molar mass. So since this was chlorine, the molar mass is 2 times 35.45, which is going to be 70.90 grams per mole. So if we wanted to turn this number into grams, we could do that. Oh, I guess I should account for sig figs, huh? I'm seeing 3, 3, 4, and 5, so we're going to want 3 sig figs at the end. Of course, because we have moles, we're going to put grams on top, moles on the bottom. Make sure they cancel out. And if we do this math, we're going to get 70.9. Doing this, we get 3.163 grams. And so, because I should round that. And so this effectively is telling us there are 3.16 grams of chlorine in 1 liter at STP. The density is 3.16 grams per liter. Hooray! There is another way we could have solved this, by the way, perhaps a little bit faster. But we'll hold off on that for just a second. How are we feeling with this one? So I wanted to do this one so we could understand a little bit more about like problems that seem simple. Just one sentence barely even took more than one line to write out, but had a bit of trickiness going on in it. So we kind of had to, break down this grams per liter idea into remembering that it's grams in 1 liter. So otherwise, we would have trouble figuring out what the volume was. Of course, you could have also just chosen a random... Oh, awesome. Yeah, so we could have chosen whatever volume you wanted, and then just divide by that at the end. That would work too, but it's just easier to start with 1, so we don't have to divide anything. So whenever you have kind of conceptual questions, I don't know if this is necessarily conceptual, but you can always plug in fake numbers. So you could have put whatever liters you wanted, and then you would get that many, you would calculate how many grams in that many liters, and then you could reduce that into grams per 1 liter. So that would work as well. Okay, so let me show you the alternative way here. We might remember STP gives us 22.4 liters per mole of a particular gas. And so, if we can convert this part to grams, and then just flip it over, we would have our answer. So, if we were to do that, and then just kind of flip it over. Let's see if we'll get the same number. I hope we do. So 70.9 divided by 22.4. Woohoo, lo and behold, we would get, so 70.9 grams divided by 22.4 liters is equal to 3.165, which we would round to 3.17 grams. Is that what we got before? Essentially, just some sig fig stuff there. So slight rounding gives us a slightly different answer because this 22.4 is rounded. But lo and behold, there we go, shortcut. So remembering your molar volume at STP, we could translate that into grams instead. Coolio. So that would be another way to potentially solve this. So I just plugged in the molar mass and then flipped the whole thing over. Yeah. So we would have gotten liters per gram, but since we wanted grams per liter, just flip it over. That's all we got to do. Okay. Here is a pretty picture for you guys. Okay, let's assume these squares are the same size because I'm such a good artist, and clearly they are the same size. But let's see what happens if we mix two gases together. So our fun fact first. All gases will completely dissolve in all other gases. So luckily for us, anytime we have a mixture of gases, it is always going to be homogeneous. Meaning, like air, for example, we have oxygen, nitrogen, water, argon, carbon dioxide, whatever, methane. It's all in there. It's all pretty well mixed together. So that's a fun fact for you guys. And let's just say, for ease of calculation, the pressure in this container was 3 atmospheres. And for the green one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say this one had 10 atmospheres. And so, if we were to put these together in the same tank, our total pressure would be the combination of the two. The reason for that, because these gases all dissolve in each other, they're just going to kind of go in there and do their own thing. Remember, gas particles don't interact with each other, so it does not matter what your gas is. And speaking of that, remember that for our ideal gas law and all that stuff, it doesn't matter what our gas is. It could be any of these. It could be chlorine, it could be water, it could be carbon dioxide, argon, whatever. It does not matter. So the pressure exerted by any gas, we can add them together if we put the gases together. So essentially, we're just adding more moles to our container. And that's it. So we're going to see that in a mixture of gases, each gas exerts what's called a partial pressure proportional to the relative amount of that gas. I know sentences can be weird, but let's say we have, here is our tank. If we say the total pressure of this is 10 atmospheres, giving that to you, we could find the pressure of the blue gas and the pressure of the green gas. So if we look at the number of blue particles, I see 4 blue particles in this container, and we have 10 particles overall, right? We have both blue and green, we have 10 overall. So that's going to tell us, let's see what color, let's use purple for this. 4 blue for 10 total particles times 10 atmospheres. Let me just erase this for now, which is just going to equal 4 atmospheres. So the blue gas is contributing 4 atmospheres of pressure to this container. And we're going to see the green gas is going to exert, oops, no, I want black, there it is. We have 6 green particles for our 10 total particles. Our total pressure. And so for the gas, for the green gas, we're going to have 6 atmospheres for that one. All right, and so of course it's not maybe this simple where we can just count up the number of molecules. A more formal way to go about describing this is the pressure of your, what gas shall we say? Well, let's just say gas A, whatever that happens to be, is going to be the moles of A over the total moles times the total pressure. So if we say these dots represented 1 mole, we're saying we have 4 moles of whatever the blue gas is and 10 moles total. So that's what we're doing here. And we multiply that by the total pressure. And so this would be kind of how we would figure out the partial pressure of a particular gas. This is something, by the way, called mole fraction. Typically, we're probably not going to see this again until Gen Chem 2, but just so we know, that is a term that exists. It's the moles of whatever you're dealing with in relation to your total number of moles. By the way, this thing is called Dalton's law. You do not need to remember that. I do not ever want you guys to focus on some random scientist's name. That does not help you understand the concept whatsoever. So the point is here, depending on how much your gas makes up that mixture, it will exert a pressure proportional to that amount. So if you have a very small amount of moles of a particular gas, it's going to have a low partial pressure. If the gas you're looking at has a high proportion, we're going to see that's going to contribute a lot of pressure. And so if we think about it in terms of air, we know that air is, let's see, 78% nitrogen, 21% oxygen, 1% argon, and the rest whatever small trace amounts. For 1 atmosphere, the pressure of nitrogen is 0.78. And the pressure of oxygen is 0.21. And of course, then the pressure of argon would be 0.01 atm. So exciting, I know. Doesn't seem terribly useful to us, but especially a lot of you going into healthcare, you're going to deal with a partial pressure of oxygen all the time. That is your PO2. You probably have it in different units than atmospheres, of course, because you're going to be dealing with millimeters of mercury instead, or torr, I guess you could use. Either way, but this is a very common figure in medicine. So you're looking at the partial pressure of oxygen in someone's blood, or oxygen saturation, or partial pressure of carbon dioxide in someone's blood. You are going to be using these partial pressures. And also it just allows us to do calculations if we wanted to figure out some fun stuff. Alrighty. So let's see what that fun stuff might look like. Okay, here we go. So, if a gas, or if a container, if a 15-liter container what's another gas we should use? How about neon? Why not? At 30 degrees Celsius, we could find the partial pressure of each gas in this particular tank. So looking at this, we have some numbers here. Two numbers should be pretty easy for us to deal with. We of course have a volume and a temperature. We're missing kind of two other quantities, right? We don't have a moles necessarily, and we don't have a pressure either. So we could do this in a number of ways, but easiest way to do it would be to look at each gas by itself. Let's take our helium first. And remember that grams and moles are interchangeable, right? We can swap them out using our molar mass. So we could convert this into moles, right? So 3.8 divided by 4.003 is 0.949288 moles. Looks like we need 3 sig figs there of helium. And so we could just calculate the pressure using our ideal gas law. And since we're solving for pressure, we're going to want to isolate that. And so that is going to be, I definitely do not have room to write that on that space. 949,288 mole. R, of course, our gas constant. And the temperature, oops, I forgot to convert it. That's going to be 303.15. divided by the volume, which was 15 liters. Doing all this fun stuff. Times 303.15 divided by 15. Doing this fun stuff, we're going to get the partial pressure of helium is going to be 1.57, and it looks like we need 3 sig figs, so it'll be 1.57 atmospheres. So that'll be the partial pressure of helium. Okay, so if we were looking now at the other gas, we would just do the same thing. We would solve for the pressure for that one, but we would use a different number of moles. So we're going to use this 16.24 grams. We're going to need to convert that to moles. What was the number? 24. I do not have neon's molar mass memorized, so let's go ahead and look at the periodic table real quick. Looks like it is 20.18. So we're just doing exactly the same thing, but for the other gas. So we get 0.0 or 804,757 whatever mole. And we're just going to do the same thing. If you do your calculations, I'm going to just do it real quick for us. Since everything else is the same, I'm just going to go ahead and not write it out. So doing this one, we would get 1.33 atmospheres. Okay, and so if we're looking at the total pressure then, actually, did I just ask you for the partial pressure? Oh, well, lo and behold, I did. But, so technically we're done. Oh, well. So for helium, it was 1.57. For neon, it's 1.33. For fun, you can see that the total pressure is going to be both of these pressures put together, which would be 2.90 atmospheres. So the entire thing would be 2.90 atmospheres if we wanted to figure that out. We could also have converted both into moles and added those together and gotten the total pressure that way as well if we wanted to. I guess I kind of wanted to do the total pressure, but I wrote the wrong question, so lo and behold, we did a different problem than I wanted to, but that's okay. That is just fine. If we wanted to solve for total pressure but right away, we could have added our moles together of our gases and then just plugged that into the ideal gas law. That would have worked as well. So remember that pressure of whatever gas A, is proportional to is going to be, you can plug it in for the ideal gas law by itself. And so we could do the same thing with the total moles. But remember, because our identity of gas does not matter, the gas law works for all the gases. They all behave the same way. At least that's how we tell you right now. Once you get to 111, then reality hits a little bit. But for right now, this will do it for us. So remember, the total pressure is always the pressure of all your gases in there combined. And that's always proportional to the number of moles of each one. For fun, let's see if we can find the mole fraction of each one. We could do that too. We could go ahead and put our moles together. So I'm just going to say 0.949. I'm going to kind of ignore sig figs for this part. If that's okay with everyone. And then 805. So these would be the moles of helium and the moles of neon. So the mole fraction of this, while we're here, we might as well just do a bunch of calculations for no good reason. 0.949 plus 0.805 is going to be 0.541. There's no units for this, it's moles over moles. So the proportion, we're going to say that helium, I mean, this is another way of saying helium is we could say something like this. If we wanted to convert it to a percent, we could do that thing as well. So just showing some of the fun stuff we can do with this idea of mixtures of gases. Let's see. We could also do mole fraction, by the way. We could have also done it in terms of pressure, which is pretty cool. So remember that the pressure is always proportional to the moles. So we could have just done that by itself. So we could say the pressure for helium, which was 1.57. atmospheres, 2.9 atmospheres. If we do that, I really hope it gives us the same answer, because it should. Yep, lo and behold, we get 0.541 again. So you can deal with mole fraction by doing the moles, but remember, since pressure is also proportional to moles, we could use the pressure too if we wanted. So, hooray, same thing. So again, just illustrating this idea that because moles and pressure are related to each other, we could use either one to solve for this. We get the same answer. Ooh, isn't that fun? Lots of information there. Okay, let's do one more problem maybe. Just to kind of illustrate this. I'll be putting your homework up probably today, so you guys can have a look at that. All this fun gas law stuff. We are gonna have, so we do have an exam next Monday. That's gonna be on whatever we finish by Wednesday. So there may we're gonna start our next chapter tomorrow, which is on solutions, which is chapter 8. Yeah, 8. Trying to keep track of this. Chapter 8, we're gonna start tomorrow. However much we get through, that will be fair game for your exam, as it were. So do I want to make your homework due Saturday then? Yeah, I probably do. So you guys can take a look at the keys. Well, I don't know. I'll ask you guys what you want to do. If you want to do on Saturday, so you could look at the exam key or homework keys on Sunday, and have that kind of inform your studying for the exam on Monday, or we could just make it due Sunday and the keys come up Monday morning, so you could spend the first part of Monday looking at that or something. So we'll put that out there. But let's do some more of this gas stuff. Let's do another one. The answer is no. No for what? Sunday, please. Make it due on Sunday? All right, well, we'll put the poll up. We'll see what people say. I'm fine with either one, so whatever you guys want to do. Okay, so if we go ahead and look at another one, let's say we have a tank of equal parts argon, oxygen, nitrogen, and xenon. The tank is 28.6 liters. And has a pressure of 200.6 atmospheres. And the tank is at 12.5 degrees Celsius. Alrighty, so we have a gas tank, as always. In this case, it is filled with a mixture of equal parts of argon, nitrogen, oxygen, xenon. We have a volume for the tank and a pressure, as well as the temperature for this tank. And so we're looking for how many grams of each gas. So notably here, we're really solving how many moles of each gas we have first, and then we're going to convert that to grams. So remember, whenever we're dealing with grams, we got to deal with moles first. So, looking at this is telling us that we have a total pressure, right? Which is 200.6 atmospheres. And so, if we want to figure out each one, we're told that this is equal parts. So if it's equal parts, what percentage or mole fraction would all of these gases be? If we've got equal parts, yeah, they're all 25%, right? Because we have 4 gases total. If they're equal, then that means it's all going to be 25%. So mole fraction, by the way, is represented by an X, or is it a chi? Well, fine. Let's just do it this way. So the pressure total, or rather the pressure of argon, should be equal to the pressure of the other gases. This is our mole fraction, right? AKA our percent of what they are. And so the pressure of all of these gases is going to be, why did I make this such a difficult number? It's going to be 50 point something. 200.6 times 0.25. 50.15. Oh, I could have done that in my head. Shame on me. 50.15 atmospheres. Alrighty, so we can go ahead and now that we have a partial pressure, we could go ahead and use our ideal gas law to figure out the moles, right? So our moles is going to be the pressure of argon times the volume over RT, right? So that should be partial pressure of argon. Volume is 28.6 liters. And of course we have our ideal gas constant, universal gas constant. Oh, I didn't do the pressure or temperature. I should just give it to you in Kelvin, save myself this math. 273 plus 12 is 285.65. So that times 28.6. Let's just do the math real quick. So it looks like the moles of argon is going to be 61 point whatever, all that fun stuff. And so if we wanted to go ahead and figure out the grams of argon, periodic table is what we will need. Argon is 39.95. Times 39.95. And so that is going to be 2,444 grams, which rounds to 2440 grams of argon. Now, will we have to do this for all of them? Presumably. Oh, duh. V over RT. If we do this, it is what was the temperature? 285. Oh, wait. Equal pressure means equal moles. So we don't have to waste our time doing this over and over and over again. We don't have to keep doing the ideal gas law. Because they are equal, we already said it's equal parts, that means the moles are equal, right? We don't have to do all this fun stuff. So we know that the N of nitrogen will also be 61.1887 moles. So we would just need to go ahead and multiply by our molar mass, which is 28.02. And that's going to be 1710 grams. What were the other gases? We had oxygen and I don't even remember. Oxygen and xenon. Okay. Do this for 32. 1960 grams. And then for xenon, we would do the last one. I would have to look xenon up. 131.3, let's say. is 8,030 grams. Ooh. So we have this big old tank that is full of all these gases. So we have figured out how many grams of each gas we had in that tank using this idea. So we had all of those. Alrighty, so it kind of made it easy that we had the same number of moles of each one, right? Makes stuff a little bit easier. However, if your thing was not the same, you could still use this idea of mole fraction to kind of get around doing it so you don't have to do the ideal gas law so many times. If you find the total pressure, if you have your total pressure of gas already, you can just solve for the total number of moles using that and then use your mole fraction later. So we could have done this ideal gas law. Instead of putting in the 50.15, we could have put the 200.6 in there. And that would be the total moles of all of them. And then we could use that mole fraction idea to find the other bits. So if they weren't equal, we could do that. So that is one more way we could get around doing this fun stuff. Alrighty, so we're going to have some homework. Hooray. I'll post that on Canvas for you guys later today. Tomorrow we're going to start our chapter on solutions. Are you guys going to want to do a review on Thursday? I'll go ahead and write to the Discord. Think about it if you want to. We can maybe go over some problems, whatever you guys want to do. We'll work that out. And yeah, otherwise we'll be good to go. All right, Shari says yes, so we'll be there on Thursday. Okay, sounds good. So the exam, just so we know, is on the solids and liquids chapter, which was the intermolecular forces. It's going to be on gases, and it's going to be on however much of solutions we cover by Wednesday. Okay, so we may be able to cover the entirety of solutions by Wednesday. It's not a very long chapter compared to some of these other ones. So yeah, we'll get through that then. And then we'll have homework for gases. I'll put that up today. We'll have homework for solutions. I'll probably put that up tomorrow or Wednesday. And so those will both be due this weekend, and we'll have fun with those. And I'll put up a key, of course, for the intermolecular forces once I get through that. Alrighty. Well, in that case, I will see you all tomorrow. Have a lovely day. Send your thoughts for the 111 students. They have their exam 3 today. So they're going to be crying. So send them your goodwill. Alrighty. I will see you all tomorrow. Alrighty. Take care.